Hi, and a pleasant evening to each and every one of you. This is Isshi Tomogdon Cuizon, and tonight I will discuss about the 5-point geometry, which was one of the topics that was given last week. But first, let's have a review about the point and the line. It says here that the point is a dot in a particular spot or surface, and a line is a straight or a curve connecting all points. We all know that these two are very common in almost any field, and I know that all of you probably get the idea of the whole picture, but it is very important for us to freshen our minds before even diving to the core. So moving on, we have here the definition of the finite geometry. So finite geometry is based on a set of postulates and defined terms and defined relations which limits to the set of all points and lines to a finite number. When confined to a plane, all finite geometries are either projective plane geometries with no parallel lines or affine plane geometry with parallel lines. So from the word finite, it would mean being countable. Under this, we will have a certain number of points, lines, and so on. There are also different types of finite geometry, and these are the 3-point geometry, the 4-point geometry, the 4-line geometry, and of course, the 5-point geometry. So basically, our topic is just an extension. So without further ado, let's go straight into it. So 5-point geometry. First, we have here the axiom. So axioms are mathematical statements that are accepted without proof. And some books use the word postulates instead of axioms, but both are essentially the same thing. And here are the 3 subpoints about an axiom. Point 1. An interpretation that produces an axiom true is said to satisfy only that axiom. It just means that in a set of axioms of, for example, the 5-point geometry, if one of it is proven, then instead of satisfying all of the axioms under 5-point geometry true, it instead will only satisfy itself. Next, point 2. An interpretation within which every axiom in a system becomes true made the system satisfiable. So if all the axioms is proven true, then the system of this whole 5-point geometry thing is made satisfiable too. Then lastly, point 3, an interpretation of the system that proves all axioms are correct statements is itself a model. In other words, after proving just one, then proceeds to proving it all, makes the system satisfiable. And if the system is satisfiable, then we have a model. Moving on, we have here the roles of the play. So some books refer the axioms as the roles of the such play because each of these has an act to play to create a model, and so this leads us to the 3 axioms of the 5-point geometry. Axiom number 1. There exists exactly 5 points. Axiom number 2. Every pair of distinct points is on exactly one line. Axiom 3. A line contains a pair of points. And if you had been studying about this, you may have had noticed now that the axioms 2 and 3 is the same as to the axioms of the other types of finite geometries. And it's true because only the first one had been changed just so it will fit the 5 in the 5-point geometry. And so now let's prove the 3 axioms. So here, axiom number 1. There exists exactly 5 points. So 5. Here we have 1, 2, 3, 4, and 5. Oh, it won't, right? Wait. Oh, how come? Oh, good. So we have 5 points. And since we now have the 5 points, then we can prove, or we can say that this axiom number 1 is therefore proven. Next, axiom number 2. Every pair of distinct points is on exactly one line. So here, we just have to draw and remember the review a while ago. It doesn't have to be perfectly straight or perfectly curved as long as it is a line that connects 2 points. Let's change the color of the pen first and let's draw a line. So point 1 to point 2, let's connect this. 1. Then here, same goes as here, and again and again. And here, and with that, we can say that axiom number 2 is therefore proven. Now here, axiom number 3, a line contains a pair of points. So as you can see, only the ends of the line get the points. Wait. Only the ends of the line got the points. And since there are 2 ends, then axiom number 3 is therefore proven. Like, there's no end here, right? And this 1 and 2. So axiom number 3, a line contains a pair of points, is now proven. So just from this, we can now see the picture or the model of the 5-point geometry. Intersections does not count as point. Think of it as these are 3-dimensional figures, so no part of the line other than the ends meets each other. Remember, some lines pass under or over others and show no incidence in order to fulfill the axioms. So we should remember this. No incidence. In this first figure, the star-shaped thing is shaded, just so it will be emphasized that this figure is not flat. Also this one, but it's not the square one. This one that crosses must not also be flat because this is a pyramidal figure. And then this one, this tetrahedron is also shaded here just to show that this figure is also not flat. Because these three are 3-dimensional shapes. Now, for the last part, the theorems. Theorems are the other statements of the system that came as the logical consequences of these axioms. So as you have just learned, there are 3 axioms that supports the 5-point geometry, and now these axioms are the reasons why there are these theorems that came out. So when you say logical, we just cannot avoid it, and same as what we did with the axioms, we should also prove these theorems. So, theorem 1, each diagram has 10 lines. Theorem 2, each axiom is incident with 4 lines. Ready? Let's prove these theorems. Theorem 1, each diagram has 10 lines. So for this theorem, if you wish, you can draw the figure again and then count how many lines are there in the figure. But I got an easier way for that, and that is through combination. The formula for combination is n factorial over r factorial times n minus r factorial. And so for n, let's write first. N will have 5 because in a 5-point geometry, we have 5 points. And then r, let's have 2 because in order to have a line, in order to have one line, you need 2 points. And then substitute this number to the formula. We'll have 5, factorial over 2 factorial times 3 factorial. 3 factorial came from n minus r, which is 5 minus 2, so we have 3 factorial. Then factor it out. 5, 4, let's stop to 3 factorial, and then 2 factorial, and then 3 factorial here. Cancel, cancel, and since 2 factorial only has 2 times 1, let's just cancel this 2 with 4, and then 2 becomes 1 and 4 becomes 2, and 5 times 2 becomes 10. Now we have the answer. So theorem number 1, each diagram has 10 lines, is correct. But if you want to check it a little bit further, we can draw it too. Let's use blue pen. So here we have the figure. Let's draw and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's it. Theorem number 1 is also proven. Each diagram has 10 lines. Let's check this. Now let's go to the second theorem. Theorem 2. Each axiom is incident with 4 lines. So since we did combination with the first theorem, let's also do permutation with this one. But first, let's erase this. We'll just stick with the values 5 and 2 for n and r. But for the formula, let's use the formula of the permutation, which is n factorial over n minus r factorial. So we will have 5 factorial over n minus r, which is 5 minus 2. We have 3 factorial. Then factor it out. 5 times 4 times 3 factorial. Let's stop there. Over 3 factorial. Cancel, cancel. Left with 5 times 4. That is 20. Now you ask me, why do we have 20 as an answer if the theorem states that each axiom is incident with only 4 lines? Well, that is because we are not yet done with the solving. Because from 20, we'll do another operation. Let's erase this first. And remember, it's 20. Then write again. 20. The operation is division. Divided by, and how many points there is with a 5-point geometry? There is 5. So 20 divided by 5 is 4. That's correct. Each axiom is incident with 4 lines. You still want me to prove it? Here. Let's count the lines here in just 1 point. 1, 2, 3, 4. So in this point, there are 4 lines. And that's how our theorem 2 is proven. And that's it for tonight, everyone. I hope you learned something new from my report, and I'm very hopeful that you did enjoy it. Thank you, and may God bless each and every one of you.